Okay, I'm going to try this again. I recorded a video and the audio did not pick up, so I'm going to try this again and I'll just summarize the worksheet that I've posted here. I'd gotten some questions on problems like 20 and 21 from the practice test, how we compute the area between two curves. And so what I'd like to point out here, or just remind you at least, is that when we use integration, we're essentially finding the area between a curve and the x-axis. And so here's our x-axis. I'll try to exaggerate it some. And we've got this upper curve, and this one's pretty easy to spot. This upper curve is generated by this equation. So I'm going to call this one area 1. The area associated underneath this curve, but still above the x-axis, is found right here. The area in the lower curve, now this lower curve, calling it a curve even though it's a straight line, this lower curve was established by this equation here, so I'm going to call this guy A2. When we calculate the area associated with this second location, we'll still use integration to do so, but we've just got to be aware that this area is going to be computed as a negative number because this area is below the x-axis. Any accumulated change or area beneath the x-axis is going to be determined as a negative number. And so what I'm saying here at the very top of my work is that the total area is the result of area 1, the top positive area, minus area 2. And I'm saying minus area 2 because I know that area 2 is going to be calculated as a negative number. If I took area 1 minus a negative number, that end result is going to be the sum of the two areas and ultimately the total area in between those two curves. Now, where that gets kind of interesting and I would argue helpful in this case is that both areas share the same boundary values. In both cases, we're evaluating this integral from -4 to -1. And because these two area integrals share the same boundary, we really could combine the two functions. And that's exactly what I'm showing here in this next step. This expression calculates area 1. This expression calculates area 2. And you'll notice that I'm subtracting them. But in reality, since the boundaries are the same, I can just as easily combine this into a single function. So 4 over x squared minus -4 is the same as +4, and I'll go through the same process as usual to find the antiderivative and evaluate at our two positions. So I chose to write 4 over x squared as 4 times x to the -2nd power. That allows me to use the power rule pretty easily to find the antiderivative, and we go through the process here. Evaluate this antiderivative at both -1 and -4. We evaluate at -1 first, and then at -4 second, subtracting in between. And during that process, we identify the total precise area between these two curves to be exactly 15 units. So I've provided a PDF copy of these notes. You can look through them a little bit more carefully if this video didn't suffice. So go back and take a look at them. But I'm going to jump down to number 21, and I would complete it exactly the same way. The problem with 21 is that it may not be immediately obvious which function is on the top and which one's on the bottom, which function is used to establish area 1 and which one's used to establish area 2. Fortunately for us in this case, we have a positive quadratic function, and then we have a negative quadratic function. Of course, the positive quadratic function is the one that's going to generate the upward facing u, and the negative quadratic function is the downward facing u. If they're both facing in the same direction, well, then it may take some guessing and checking to determine which one's on the top and which one's on the bottom. But that is very important for us because, again, the area associated with the upper function is considered positive and the area associated with the lower function is negative. And we have to subtract in that order specifically in order to make this work. So applying the technique from before, I immediately recognized, well, I can use a single integral and subtract the two functions. So here's the area 1 function, and I wrote 1/2 x squared instead of x squared over 2. So this original a1 function, the a2 function, subtracted and combined like terms. And now when I find the antiderivative of this expression using the same techniques as before, albeit a little bit more difficult because of the fractions involved, but still the process is the same. We can find the antiderivative, simplify, and evaluate at two different values, -3 and -4. Now, this particular example is a bit more challenging because of the fractions, but do remember that calculators are permitted on this test. I just don't want you to use the integral capabilities of the calculator if you're using one that has that as an option. Use the calculator just to simplify your computations, not to perform the calculus tasks. And now, as it turns out, after simplifying all of these fractions, the result comes out to be 35/6 or 5.83 repeating. And I believe both of those answers do match the answer key. If you've got further questions, please let me know. Thanks for watching.